Okay, greetings, one and all. Alright, so as I promised, I would have gone through logic gates. So I'm going to split it in two sections. Alright, I'm going to give you the basics as just theory, and then part two we will be doing I'll be using FET to make the circuit to show you what the logics are. Okay, so without further delay, it's electronics, and we're talking about logic gates. As I said, it's a very simple logic gates. I'm not anticipating uh, any 1 hour or 2 hour videos. So let's get into it. Alright, so we have what we call the AND gate. Alright, and in the next in part 2 I'll show you what the logic gates look like. But logic gates basically is a semiconductor, okay, and the semiconductor um, is they use um, components, right, to put into a chip. So the logic gates are sold as chips, and as I promised that you will see a picture of the AND gate, the NOT gate, and the other logic gates as they are in real life. This presentation focus on the basic principles that govern logic gates. Good. So we're talking about AND gate, which is my first choice of gates, and the AND gate is similar to that of a series circuit, right? And we know in a series circuit, all two switch must be turned on, right, for this light to be in operation. Now, when you want to represent um, an AND gate, we would use this diagram as you're seeing AB. So switch A would be input A, switch B would be input B, and the output Y would be the lamp. Good. Um, as we go along, I'm going to integrate some things. Remember, a resistor is placed in series right here to protect the LED, the light emitting diode. All right. Now, to show the operation, what happens when both switch are open. When both switch are open, no current is going through, no voltage is observed, so we call that zero. In logic gates, we deal with one and zeros. Zero mean off, one mean on, right? So to see the logics of operation when one or two switch are open or closed, and when the LED is on and off, what we do, we use what we call a truth table. Now, I need you to pay keen attention to the truth table, which, if this should come in an exam, this is an easy giveaway. If they ask you to write the truth table for a AND gate, because this is what happens. Always try to memorize or to visualize a series circuit. If both switches A and B are off, meaning they are at zero, then the light will not come on. Good. If I should close A only, right, the current will go around the circuit, but what will happen? It will be cut off at B. It does not have any path to go, so the light will still not turn on. If I should close switch A and still have switch B open, we still see the problem. By the time the electricity reach here, it will not have any path to go to complete the circuit, so the light will remain off. And basically, that's what an AND gate is. It is a series. It behaves as if the logics behind it is a series circuit. Both switches must be turned on so that you have a complete path for the current to go travel around the circuit so that Y can be turned on. Alright, you could have a lamp here, you could have a LED here, you could have a motor here, but at the end of the day, both switches must be turned on, and that is what we say an AND gate is. A and B must be on. So that's where the logic of AND is. A and B must be turned on for the light to be on. Alright, you can't have 0 or 1, 1 or 0, 0 and 1, or whatever the case may be. Now, I need you to know something. Notice how the values are set up in this table, right? You could either start with 1, 2, 3, 4. You have 2 to start off with, 2 zeros, then 2 ones, and then over here you alternate. So you could have 0, 0 on this side, 1, 1. If that's the case, if you're putting this pattern on the left side, on the B it's going to be 0, 1, 0, 1, alternate. But in this case, what they do, they alternate here first, and then what they do, they split the total number in two. In the sense, you have 4, so we have 2 zeros, 2 ones. Good. So you can do it, you can follow this principle when you write in your table. You can either start by alternating the ones and zeros, 0, 1, 0, 1. The second, you have 4 possibilities. So what you do, you put 2 zeros and then you put 2 1. Alright, so that's it for the AND gate. Now, what about the OR gate? What is an OR gate? The OR gate behaves as if it is a parallel circuit. Alright, and in the parallel, in depicting or to symbolize the OR gate, it is similar to that of the AND gate. It's just that it's like an arrowhead. But it's like an arrowhead. So this would give you this is a symbol for the OR gate. Now, moving back over again to the truth table. And the truth table, as we see, as I said, what you want to do, your inputs, right, which would be switch A, input B, which will be a switch B. What you want to do, you want to alternate your variables, your zeros and ones. So I have 4, so I'm going to alternate it 4 times. 1, 0, 1, 0, 1. I have 4 spaces. For B, what I do, I say, alright, I have 2 zeros and I have 2 ones. And this is what you'll see come out. Now, if both switches are off, then the light will not come on. Therefore, at the output, you will have 0. Nothing happened. Now, if I have 1 and 0, then I'll see I will see the LED lights up. If I have A off and 1 and B on, I'll get the light to light up. And just to backtrack a bit, if I close this, then the current will meet this part around here and complete the circuit. So Y will still light up. Now if I close B, what will happen? The current will take this direction. Let me go again. If I close A, then the current will take this path. Yes, good. And if I close B, that's 0, 0 meaning A is open, B closed meaning it's 1, then the current will take down this path downstairs and then go up, complete the circuit. Now if all switches are closed, what we have all ones and then the output is 1. Alright, do not try to swap the truth table, try to know the principle. Alright, so if I have if A or B is on, then the light turns on. Hence what we say the OR gate. Good? Now we have the NOT gate, and it means it is not what you put in. Good? The output will not be the same as the input. Good? And we see what we do, we put two resistors, right, in series, and then we put the switch between both. Right? Now what you will see happen is this. Now let me show you the symbol for a NOT gate before I explain that. That's a symbol, and let's go to the truth table. Now if I turn on the switch, right, if I turn on the switch, if switch A is on, right, what you'll notice is that the electricity, the electric current will move this way, and nothing will reach the lamp. Hence, if A is closed, then nothing will reach Y. Now if I open it, then what you notice, the path of the current will take this will be the path of the current. So Y will be on, which is 1, while A is at 0. I will repeat. If I close A, then A will become 1, and we will see that electric current is moving around in this circuit area. Now, if I should close A, then A will be 0, and you'll see the current going around, going to Y, go through Y lights up, and then we are good to go. Right? Now, let's go. So let's talk about, you can have an AND gate, and then we could make the AND gate not operating as itself. And if we have a not AND gate, we call it a NAND gate. Good? And that's it. What you do, what would happen is that we'll have two switches in series of each other, right? But these switches will be parallel to the output Y, which is the LED. Now this is what a NAND gate looks like. Good? And you will soon find out what the node right here means. Now this is what happens if both switches are on. Then you'll notice that the current will go here, making the circuit operate in normal operation, right, where the Y is on. Now if we have A on, right, what will happen is that the current will not go through. Alright, now but Y, the output, will still be on, because the current is moving along this direction. It is not accepting the cutoff in current or the short circuit. Good? Now B could be on, and what happened is that the current still has this gap here to come across at A, because A is not closed. Now if we should close A and B, then we will notice that the output Y is off, and the current is traveling in this little section here, right? Now what is the NAND gate? Right, it is a AND gate, right? It is an AND gate, and you attach a NOT gate to the AND gate. Good? So A and B comes out, right? A and B comes out, and then whatever goes in, what comes out of A and out of the NAND gate, of the AND gate, sorry, it goes into the NOT gate, making it not the same as the input. Good. So if 0 and 0, we see where 0 and 0 gives you 1, right? Now here, this is how we would look at it. 0 into turn on switch A, you leave switch, turn off switch A, turn off switch B, your output is going to be 0. If I turn on switch A and leave switch B on, I still have an output at 0. Now if I turn on A and leave B off, then I still get an output at 0, right? All switches must be on for you to get the one here in an AND gate. In an AND gate. Good. Now what you'll do now, you'll put all that output, which is Y1, as the input for the NAND gate, and what you notice, where 0 comes out, you have 1, goes in, you have 1. When 0 goes in, you have 1. When 0 goes in again, you have 1. And when we notice that when 1 goes in, then we have 0. That is when all these switches are on and the output Y is not getting any electricity. Now for our last gate, which is a NOR gate, which is mean it's not a OR gate, what we want to do is to take the switches out of series, right? We're going to put them in parallel to each other, right? This is what an OR gate looks like. Let's look at the truth table, right? If I turn off both switch, then the electric current will go here. Now if I turn on A and leave B off, this LED won't get any current. Now if I leave this open and I close switch B, then I get nada, nothing at all, nothing, because the electric current will go here, circle around here, leaving the output Y not getting any electricity. So we have 0. And if all switches, we still won't get any signal from the LED. Now NOR gate is basically having an OR gate. The NOR gate is basically having a not OR gate, sorry, and you connect that to the NAND gate, right? A and B representing switches, right? And you notice what you need to do now, the output, because if it was the OR gate, we know that the output will be if any one switch is on, then you're good to go, right? But all that input, when fed into the NOT gate, you're going to get the opposite value, right? And this truth table basically shows you. So if I open both switches, right, that's the only case or state in which the Y will get electric current, right? If I close any of them, right, if I close any of them, that section that I close will get the electricity, the electric current flowing. Alright, and that's basically it in a nutshell.